Today on How It's Made. Innerspring Mattresses. Stand-up paddle boards. And vacuum cleaners. An Innerspring mattress is made with steel wire springs to support a person's body weight. The quality of the mattress is usually determined by the thickness of the steel wire, the number of springs, and how the springs are configured and linked to form the inner support system. Most of this Innerspring mattress is crafted by hand. The material in between the springs contains multiple layers of batting made from a blend of polyester fiber and organic cotton fiber. Cotton allows the batting to be breathable, so the mattress won't trap body heat. Polyester prevents the cotton from matting, so the batting doesn't flatten over time. This machine feeds both materials to a carding machine. At the first station, rollers and cylinders with metal teeth open and comb out the fibers. Next, the blended polycotton is formed into a thin, fluffy sheet. The next station layers the sheet. Rollers compress the layers to form a thicker sheet about 2 3/4 inches high. The machine cuts the sheet to the width and length of the specified mattress. A technician places the finished bat on a scale to ensure it hits the target weight. He piles 18 bats on a cart, which is how many are required for just one mattress. Meanwhile, another technician builds the mattress's support structure known as the inner spring unit. A coiling machine pulls spring steel wire off a spool, then winds and cuts it into coils. The top and the bottom of each coil are crimped, creating interconnection areas. A technician inserts spring steel wire into a lacing machine and places a row of coils on a table. As the machine advances, the helical wire catches the coils at the points where they're crimped, lacing them together. The process is repeated until the spring structure is the size of the mattress. The perimeter of the mattress is framed with more helical wire. The fabric surface of a mattress is known as the ticking. A seamstress marks the required dimensions on a stack of cotton fabric. Using a rotary cutting blade, she cuts the ticking fabric along the marked dimensions. A sewer hems the edges of all 3 panels. This step will strengthen the connected seams. He also sews on the labels listing the product and safety information. The sidewall consists of 4 layers: the ticking, 2 types of bats, and a backing fabric. A seamstress pulls the layers through a stamping machine, which fastens the layers together with a pair of brass eyelets every 2 3/4 inches. Using another stamping machine, she attaches cord handles with large brass grommets. The handles make it easier to flip and rotate the mattress to ensure even wear. Another technician covers the inner spring unit with a lightweight fabric and pads the corners with batting to prevent indentation. He attaches the fabric backing of the sidewall to the wire perimeter of the inner spring unit with hog ring staples. He tops this side of the mattress with 9 bats, equivalent to 27.5 inches of padding. He trims each bat by hand, gradually narrowing the layers as he works his way downward, creating a tapered shape. Then a polyester fabric layer is added for comfort, and a non-woven flame-resistant barrier fabric layer on top. The ticking is put into position, and the excess filling is trimmed. The technician pulls the ticking and pins it to the top of the sidewall. He flips the mattress and repeats the process on the other side. Using an industrial sewing machine, he sews the top and bottom tickings to the sidewall with edge tape. Woven cotton ticking is more durable than knitted cotton. Finally, the automated machine tufts the mattress and inserts a woven band through the middle, locking each tuft in place with a pom-pom on both sides. This prevents the materials inside from shifting and sets the level of firmness. Stand-up paddling has become a popular sport, but paddle boards have been around for over 3,000 years. Contemporary boards rely on modern materials to make light and reliable paddle boards, suited for leisure as well as for competition. This paddleboard is made with vinyl ester resin and laminated fiberglass. It's equipped with an onboard lighting system, an anchor, and a neoprene rubber non-slip pad. In the gel coating room, a technician wipes a release agent on the paddleboard mold to make the surface smooth and clean. Another technician positions the fin channel on the mold using a thin fiberglass template as a guide. He uses an airless pumping system to spray the mold with a vinyl ester gel coating mixed with hardener. He takes a mill gauge to make sure the hull thickness is even. A technician prepares to make the first structural layer of the hull using a 3/4 ounce bidirectional fiberglass mat. First, he pulls out a panel of fiberglass and covers the gel-coated surface. Using fabric scissors, he cuts the mat and makes the fiberglass skin as tight as possible. He tears the mat to conform it to the rounded shape of the gel coat and fits the mat to the edge of the hull. He applies vinyl ester resin with a paint roller. The resin saturates the fiberglass, which merges with the gel coating. Extra material is placed over the fin channel to strengthen the structural bond between the channel and the hull. Then the technician uses a bubble roller to push out air bubbles. He applies a second coat of fiberglass to reinforce the structural integrity of the board. In the assembly room, another technician fits a template on the board deck and traces the contours of the hand grab mount with a pencil. He uses an air saw to cut out a slot in the fiberglass laminate to fit the hand grab mount. He binds the hand grab mount to the hull with a coat of vinyl ester resin. Within about 20 minutes, the laminate hardens. Next, plastic tubing for the internal anchoring system is installed. A technician applies a bonding adhesive to the tube, securing it in place. He attaches the tube with tie wraps so it doesn't get tangled inside the hull. He installs a jam cleat for the rope that will allow the paddler to manually control the anchor from the deck. The hull's cured vinyl ester resin is now firmly bonded to the structural laminate. The assembler applies expanding adhesive and positions an expanded polypropylene foam stringer inside the hull. The foam stringers are the backbone of the board. They support the weight of the paddler on the deck while keeping the board as light as possible. Using a nylon wedge and a rubber mallet, the assembler removes the mold from the hull. Since the hull is so lightweight, 2 assemblers can lift and flip it onto a cart. An assembler trims off the excess laminate using an air cutter fitted with a diamond cutting blade. He levels the foam stringers with a file blade, ensuring the tightest possible fit between the hull and deck. He applies expanding foam adhesive on the stringers before he places the deck on the foam with the help of a coworker. The adhesive quickly binds the parts together. The vinyl rub rail, designed as a side protection, masks the joint between the deck and the hull. The hull contains a dry storage hatch where the onboard battery is housed. The 8 amp-hour battery can activate the power pole, a micro anchor designed for shallow waters. In deeper waters, a paddler can manually activate the internal anchor system with a 16-foot nylon cord. Finally, this board is ready to hit the water. Invented in 1901 by a British engineer, the vacuum cleaner was considered a game changer. The original versions were made substantially heavier than the vacuums built today. In fact, they were so large they had to be pulled by horses to get from building to building. Through the magic of suctioning power, a vacuum cleaner can make dirt disappear almost instantly, really improving personal space. Production starts with the electric motor that powers the suctioning fan. A machine picks up a rotor and transfers it to an imaging system. Using a camera and laser, the machine measures the part and confirms that it's to specification. Next, an automated system attaches plastic discs onto both sides of the part. These plastic discs will serve as electrical insulators. A computerized camera confirms the discs have been correctly placed. A carrier transfers the rotor to the next station. Here, a rotary copper switch is placed onto the shaft. The switch is called a commutator. Its role is to periodically reverse the electrical current as it flows through the motor, allowing the motor to operate more efficiently. The next robot places the rotor in a device that winds thin copper wire around the part hundreds of times. These windings will be used to create a rotating magnetic field in the motor. A welder joins the commutator to the copper windings using small hooks. This step establishes a connection. A machine slides a slatted plastic cover over the rotor. The slats fit in the rotor grooves. The cover reduces the noise the rotor makes as it revolves at high speeds. Spouts drip synthetic resin onto the copper windings. As it hardens, the resin stabilizes the windings, ensuring there are no loose wires. A computerized cutting tool shaves off a small amount of the commutator, making it round and smooth. A robot then deposits the rotor on looped belts. The belts spin the rotor, and sensors detect vibrations that indicate any imbalance. If an imbalance is found, the system sends the rotor over to a tool that removes material until the part is balanced. Then it's over to another testing machine. This one probes the copper windings to detect failures using a complex measuring system. A mechanized system installs a substantial bearing on one end of the shaft. A robot retrieves it, flips it, and the system attaches a bearing to the other end. The motor housing with the stator moves into position. A machine places the rotor in the center of the stator. All the work on this vacuum cleaner motor has been done by machines. Now, a technician installs a carbon brush that will make electrical contact with the rotor. A diffuser shield is placed on the housing. Meanwhile, the computer system screws the diffuser to the motor assembly. A small metal spacer is deposited on the protruding rotor shaft. A robotic arm places the lower fan impeller plate over the shaft. The mechanized system screws the assembly together, and then the upper part is installed with the suctioning fan blades. A machine spins the fan to test it for any imbalances. Then a cutting tool removes material to calibrate the fan assembly. A steel cover is flipped into position by a platform which elevates the fan and motor assembly. Stay tuned. There's more dirt on how the rest of the vacuum cleaner comes together. While the vacuum cleaner may alarm your pet, to an enthusiastic cleaner, this is an awesome machine. Not only does it remove the dirt you can see, it suctions up fine particles that aren't visible, leaving your home even cleaner than it looks. Inside every vacuum cleaner, there's a high-speed suctioning fan. Machines test the fan for quality control. A conveyor delivers the fan to a completely mechanized system that evaluates the interaction between the carbon brush and the rotor. This final inspection ensures the vacuum fan is balanced and fully operational. A technician applies a rubber seal to the rim of the vacuum's lower housing. He inserts the power supply reel in a hollowed-out compartment. The fan is installed and connected to the power supply reel. He snaps the back panel to the lower housing. The power supply cable is plugged in for a later check. The next component assembled is the control panel. A technician screws the control panel to a mounting plate. A rubber bumper is placed along the edge of the cover frame. The cover frame is then transferred to the vacuum. A dust bag is attached to a bracket that straddles the frame. At the next station, a robotic system stabilizes the assembly and attaches the frame to the housing. Then the vacuum cleaner is released from the machine and the carrier takes it forward for an inspection. An inspector installs foot switches for the power cord and for machine activation. He tucks a filter into its slot. The cover panel now arrives via conveyor. The technician snaps it into place on the cover frame. He installs a hinged access panel, which houses the suction tools until needed. This is the final step to complete the assembly of this vacuum cleaner. Another kind of vacuum cleaner uses easy-to-empty plastic canisters for dirt collection. It uses a substantial filter to separate dirt from the air. Suctioned air and dirt spin within this canister. Larger dirt particles fall to the bottom, while finer particles become embedded in the filter. A technician installs the filter canister in the vacuum cleaner housing and inserts a nozzle accessory in a slot. Down the line, another worker installs a top plate. Next, a clear plastic interceptor is installed, which collects the majority of the dirt. The technician applies a plastic bumper to the back of the vacuum. With the assembly complete, this bagless vacuum cleaner heads towards the inspection station. Both kinds of vacuum cleaners undergo final testing. A robot plugs the opening for the hose, turns the power on, and tests every function, while a computer measures its performance. Cleared for retail, the robot removes the hose. The vacuum cleaner heads toward the packaging line. A robot lifts and carries the vacuum cleaner, stopping above a vacuum cleaner that's already on the conveyor. The vacuum on the conveyor moves forward and sensors signal the robot to set the second vacuum down. The vacuum cleaner moves along the conveyor belt into a sheet of plastic wrap, which envelops the product. Heated knives cut and seal the ends in one action. This protects it from superficial scratches during transport. A technician uses molded pieces of foam to slide the vacuum into a cardboard box. The foam pieces remain in the box to stabilize the vacuum during transport. Equipped with either a bag or a plastic receptacle, the technology is all up to the consumer's preference. Regardless of the model, each type of vacuum can make dust bunnies stuck in the corners of rooms and under beds vanish before your eyes.